Hello everyone, thank you for taking your time for this pre-recorded presentation. My name is Zhou and I'm a first-year graduate student in the Mechanical Engineering Department of the University of Wisconsin-Madison. Today I'm presenting with my colleague Wei, Rado, and Den on the topics of the simulation of robotic mechanical system, specifically wheel-terrain interaction for space rovers. So the motivation of conducting research on the current topic was driven by NASA's 2023 Viper lunar rover mission. We would like to see through a simulation framework which is easy to use and easy to deploy in order to help researchers performing various simulation on a hard-to-reach environment. The simulation framework emphasizes on two major parts: rover mechanical system modeling, which consists of major mechanical components on the rover, such as suspension system and the wheel geometry, and also the terrain modeling, which is vital for wheel-terrain interaction simulation. In this presentation, we'll discuss on two terrain models, the rigid terrain and the SCM deformable terrain model. There are also SPH and DEM methods. We have currently finished implementation, which will support high-fidelity granular simulation. Our research relies on Project Chrono, which is an open-source multi-physics simulation engine developed by the University of Wisconsin-Madison in the United States and the University of Parma in Italy. Project Chrono is a highly efficient, expandable, and modular physics engine. The core module of Chrono engine provides the most important many-body dynamics computation, which is important for the work which will be presented today. Other modules such as FSI and GPU enable fluid and granular terrain simulation. E-related and OpenGL modules support simulation rendering. Parallel modules support multi-core CPU physics simulation, and etc. We're also benefiting from the many-body dynamic simulation capability in Project Chrono. It supports the simulation of rigid bodies. It can either be meshed geometries or a preliminary geometry such as a box or a sphere. It also supports constraint modeling, which will impose trajectories between bodies. The contact force, sliding, and rolling friction force can also be simulated when collision happens using either a penalty-based SMC contact model or a complementarity-based NSC model. So we'll discuss the difference between these two different contact modeling later. And here is a quick animation showing mechanical components of the nozzle of a 3D printer. So as we are moving forward to talk about the development of our rover models, so the goal is to establish a ready-to-use library for consists of several rover models, which are easy to deploy and easy to plug into any kind of a simulation environment. So currently, at the current development stage, we have a 4-wheel Viper lunar rover and also a 6-wheel Curiosity Mars rover. The focus still remains on capturing the major mechanical components of the rover and also the wheel-terrain interaction, which will be focusing on the interaction between the actual wheel geometry, which is a mesh, and also the terrain. It can either be rigid or SCM deformable. As we are moving forward, in our next steps, we want to dig into the simulation of electric motors and also the batteries. So by digging into these two topics will allow us to discuss and research the power consumption of the rover and also to simulate the motor behavior better. The first rover model we have developed is a 4-wheel Viper lunar rover, which has a body length of 1.74 meter, a body width of 1.53 meter, and a 2.26 meter height. So the mass of the rover adds up to 417 kilogram. The major mechanical components include 4 independently controlled steering motors and driving motors, and an actively controlled suspension system. We have designed 2 wheels to be attached to the rover. One is a very detailed mesh which captures details such as the grousers on the wheel, while the other one is a simplified version, which has less triangular faces on the mesh. In that way, we can ease up the simulation by a lot. So for the six-wheel Curiosity rover, we have modeled and encapsulated a fully functional rocker bogie rover suspension system. 4 independent steering motors and are also added and can be controlled to perform all kinds of steering or turning maneuver, which will need to be performed on an actual rover. So the rover has a length of 3.94 meter, a width of 1.56 meter, and a height of 1.58 meter. Similar to the Viper lunar rover, we also added a simplified version of wheel, which can be used to ease computation and speed up simulation. So for the terrain modeling, the first option is to use a rigid body to represent a non-deformable rigid terrain. This is the simplest and fastest terrain model we can put into a simulation. The terrain can either be modeled as a preliminary geometry object or imported as an OBJ mesh. So the upper right example right here is showing a tire being dropped on a flat rigid terrain, which is basically, in this case, we modeled it as a box-shaped rigid body. And on the bottom right corner is a screenshot of Viper rover moving on a terrain mesh, which is approximately 500 meter by 500 meter. It's modeling a part of the terrain scanned by Curiosity. It's a part of the Mars terrain. So the simulation can be speed up by taking advantage of the concept of collision family in Project Chrono. So in order to simulate a large terrain, for example, in this case is 500 meter by 500 meter, we can chop a huge terrain OBJ file into pieces to eliminate subterranes which are not important in the current frame. So the collision and the simulation engine will only consider and do the computation on the subterranes which are directly under the rover. It worth to be mentioned and a little discussion about SMC model and the NSC model. So these are two different contact models that we can use. So for the SMC model follows a typical penalty-based contact modeling where interpenetration is allowed between two rigid shapes and generates contact forces based on spring damper model, where NSC, which is the full name is non-smooth contact, assumes materials are hard, no penetration is allowed in this case. And for each time step, NSC needs to solve an optimization problem underlying in order to obtain contact forces. Below is an example of a bouncing ball. The speed of the ball is shown on the right. We can see that normal force is gradually increasing to counteract the ball movement, while NSC will respond to collision instantly. So the second type of terrain that we can model, the first one is rigid, which is non-deformable. For this one, it's deformable. So it's called the soil contact model. It was first proposed by Kring and Herzinger from German Aerospace Center in 2009. It draws on the original semi-empirical terrain deformation model made by Becker and Wang. So terrain modeling is basically a vertex-based grid. If we take positive z direction to be vertically up, then x and y coordinates of each vertex are fixed, and only displacement on the z direction is allowed. The initialization of such a terrain can be achieved by either with direct initialization, basically a flat terrain, or from a BMP height map. So basically, we can import any terrain as long as we have the height map data. Also, another point to be mentioned is that the SCM model allows multiple time deformation, and it means it not only cares about the force applied on the wheel, but also the shape of the deformed terrain. So if the second wheel goes across the footprint of the previous wheel, the force can be computed correctly based on the deformed terrain. So here is the sinkage-pressure relationship equation originally proposed by Becker and Wang, where P is the computed contact pressure on the current contact patch, and Z is the sinkage of the contact patch. The Kphi, Kc, and N are semi-empirical parameters. They do not have any physical meanings. But if we would like to use SEM model to simulate a specific type of soil, we need to perform a barometer test to fit the data points obtained from sink gauge pressure testing, and the curve fit will help us determine the values of Kc and Kv and also N. So these three values are very case specific, depends on what kind of soil we are trying to simulate. Tangential stress in the SEM model is given by Genosee Hanamoto, as shown in this equation, where J is the accumulated shear, C is cohesion, V is the internal friction angle, and K is the Genosee parameter. So here is an animation of an example simulation which tests out the rocker bogie suspension system on the rover, interaction between rigid body to rigid body, which is the interaction between the rover wheel and the rocks, and also it tests out the wheel terrain interaction using the SEM deformable terrain model. The simulation is approximately 50 times slower than real time. So currently the SEM terrain is parallelized by OpenMP on CPU. Moving forward, we have planned to implement the same model but on GPU to see whether we can get better performance. In order to allow the current simulation framework to help with researchers' driving control algorithm development, we have performed another simulation test here with an uphill scenario with 15 degrees, 20 degrees, and 25 degrees uphilling scenario of the wiper rover. So the purpose of such an experiment is to check whether the current implementation and the current model of the terrain can handle slip well. So the slip ratio on all 3 degrees of uphill can be found on the right side. So the slip ratio increases as the uphill becomes more steep. The slip ratio are approximately 0.2 when it's 15, 0.35 when it's 20 degrees, and approximately 0.6 when it's 25 degrees. And here is another example which simulates a classic scenario in rover testing. So it tests the Curiosity's obstacle crossing capability. In this experimental scenario setup, we have 2 rocks represented by mesh placed in front of the Curiosity rover, and the data for vertical force on Z direction and torque applied on the left front wheel. By the way, the 2 plots are plotting data that we have obtained from simulation of the left front wheel of the rover. So these 2 plots shows at the beginning the rover is dropped, so we see the spike of Z force. We see after we drop the rover is trying to accelerate at the beginning, and we can see these 2 peaks of Z force and torque as when the left front wheel first hit the obstacle, and another peak which the left front wheel is trying to it's on the top of the rock, and it descended to the ground and it's trying to accelerate and move forward. So this is another example testing out Curiosity rover on the rigid terrain. It's a very similar scenario. Instead, this case we use the preliminary rectangular shape obstacles to represent the obstacles. So I can see similar things, but this time we're plotting the z directional force that we obtained from simulation on the left front wheel. We can see the left front wheel first hit the obstacle, and the right front wheel hit the obstacle later, and these 2 peaks are represented well. Thank you so much for taking your time looking at this presentation. I hope you have a great day. Thank you.